So we can do gas law calculations using the ideal gas law. The ideal gas law is one you've probably heard before. It makes certain assumptions of gases, but usually in most samples of gases that we use, these assumptions are very valid. The equation itself is PV equals nRT, or PivNRT. P stands for pressure, and we're going to use pressure in atmospheres as the pressure unit. It doesn't have to be, but you can always convert between one unit and another, and it's easiest to assume that it's in atmospheres. Volume using this equation needs to be in liters. N is the number of moles. T is the temperature, and it has to be in Kelvin. And R is something we call the gas law constant. The value of the gas law constant is 0.08206 liter atmosphere per mole Kelvin. Make sure you have those units. As you notice, the liters are the same, the atmospheres are the same, the moles are the same, and the Kelvin are the same. If you want to use a different unit of pressure, you can convert this value of R into a different unit of pressure. In any case, now this is fairly simple if you look at this problem. We just need to substitute in. What do we have here? Well, we have the number of moles, we have the volume, we have a temperature, which is in degrees Celsius. We need to convert that to Kelvin, and we're looking for the pressure. So, to rearrange this gas law, let's just plug and chug now. Pressure is going to equal nRT over V, or N is 0.813 moles, R 0.08206 liter atmosphere per mole Kelvin. T, well, I need to convert degrees Celsius into Kelvin. In order to do that, I'm going to take 18.6 plus 273.15, 291.75, or 291.8, since I'm going to cut off my significant figures right there. 291.8 Kelvin. And my volume is 18.6 liters. My pressure in this case, the answer comes out to be 1.05, and again, our units are atmospheres. Now, another variation of an ideal gas law problem is, well, you can solve for any of those variables when you're doing an ideal gas law problem. Again, our ideal gas law is PV equals nRT. Now, in this question, let's see what we have. What is the mass? So I'm looking right away for mass. Mass isn't in my equation. What am I going to do? Well, mass has something to do with moles. We can rearrange this equation a little bit to find mass, because I know moles, and don't forget this, moles is equal to grams over the molar mass of the substance. So now I have PV equals grams over molar mass. Grams, that's what I'm looking for, times RT. Now let's see what else we have in this problem here. At a pressure of 0.913 atmospheres, a volume of 16.2 liters, R, constant, and T, temperature of 265 K. Got to be in Kelvin, already in Kelvin. Let me put these numbers in here first. So I have 0.913 atmospheres times my volume of 16.2 liters equals grams, I don't know, over molar mass. I'm still confused. Times R, 0.08206 liter atmosphere per mole Kelvin, times my temperature, 265 K. So the thing we don't know is this molar mass. Oh, wait a second. It's the mass of oxygen. Now the gas itself matters. To use the ideal gas law, in the first problem we didn't need to know what kind of gas it was at all. It said it was hydrogen. Who cares? It didn't matter what kind of gas it is. Here, however, it does. So we're going to take the molar mass of oxygen. It's O2. The molar mass is 32 grams per mole. And so now I have everything but my grams. When I go ahead and rearrange this, and this is going to be tricky, I'm going to take this times 16.2 times 32 divided by 0.08206 liter atmosphere mole Kelvin divided by 265, and I get an answer down here 21.8 grams. Again, significant figures are always critical here, and the thing that governs my significant figures, the only tricky part of significant figures in this problem, is temperature, so be careful. And we always want to use a molar mass. Well, this is actually 32.0 with as many significant figures as we're going to need in our answer. And so we're all good. And there we have an answer. We can come up with a whole lot of different problems mathematically to use this ideal gas law.